Please welcome, from the University of Vermont, Dr. Josh Bongard.
Thank you. Thank you. Thank you very much, everybody. And first off, thanks very much to Adam and Steffi for the invitation to come and address all of the factory workers today. Thanks to the Factory of Imagination organizers for putting on such a great event. And most of all, thanks to all of you for coming and bringing your curiosity and excitement. So I'm going to tell you a little bit about my big idea today, which is evolutionary robotics. So Adam and Steffi asked us to bring our imaginations and our big idea. And I'm going to tell you a little bit about that big idea. But of course, big ideas don't come from nowhere. Mine grew over time as I grew up, and I gradually transitioned from being a student to a professor now at the University of Vermont. So what I thought I would do this morning is to explain this big idea to you by walking you through a few of the phases in my own journey on this planet so far and show you how my big idea developed. So let's start at the beginning. I was born and raised in Toronto, Canada, and like perhaps many of you as a young person, I was really interested in animals and robots. I drew robots, I created them out of Lego. I went to the movies and saw all these amazing robots doing all these amazing things. But as I got a little bit older, I started to look around and thought to myself, well, where are all the robots? If they're so useful and they're so cool, how come I don't have one at home helping with the dishes, helping to shovel snow off the driveway? Where are all the robots? That was my first question as I started to grow up. And around my 13th birthday, I got my first piece of tech, my first machine. For the youngsters in the crowd, you might not recognize this particular machine. This is a Commodore 64. It was the state-of-the-art in personal computers back in the 1980s. And I devoured this machine. I rapidly discovered that even this simple computer, which today would probably be considered a toy, given enough thought power, you could get this computer to do just about anything. It was a revelation for me. About the same time, I got my second piece of tech, which is this very fancy robot that you see here. And I started to play with this robot as well and suddenly realized that this robot was very different from a computer. I'd seen a lot of television commercials about this. I asked for it for Christmas. I'd seen all these amazing things that this machine could do. And when I got this machine, I figured out very quickly that it stank. It was terrible. There was only a few things that it could do, and those things it couldn't do very well at all. What was the difference between computers and robots? I was wondering about this for quite a while. I used these 4 photos to try and drive home why we don't yet have robots in our homes, but we now have computers in our back pockets. What's the difference between these? This talk's going to be a little bit interactive, so I have a few questions for you. And the first one is, what is the difference between the top pair of photographs and the bottom pair of photographs? If you have an idea, raise your hand, and Dan and Lisa have a microphone for you. Don't be shy. There's someone down here who has an idea. What's the difference between the top pair of photographs and the bottom pair of photographs?
Oh, sorry. It's a well-defined environment in the top.
It's a well-defined environment in the top, right? It's not an arbitrary choice that there's a picture there of a factory, right? Factories, by definition, are well-defined or controlled environments. So it's not really the case that we don't have robots yet. We do have a lot of robots. They're called industrial robots, and we've had them for a long time. Over 100 years ago, Henry Ford came up with the idea of mass production, which was a way to systematize the way that we build things indoors. And then many decades later, in the 1970s, industrial robots arrived, and they automated the way that we build things indoors. So the way that we build things indoors has changed completely over the last 100, 120 years or so, but the way that we build things out of doors has not changed that much. So now my second question to you, why don't we have robots helping us at construction sites? Ideas? Any brave volunteers? Is there one here? Right here? Exactly. So an outdoor environment like a construction site is not a controlled environment. We might want to deploy robots that do nothing more complicated than move bricks from pile A to pile B on a construction site, but every construction site is slightly different. Some have people, perhaps it's raining or it's cloudy, perhaps there's a road in the middle of the construction site and the robot needs to know something about fast-moving vehicles. The Greek philosopher Heraclitus 2,000 years ago said, man never enters the same river twice, right? So we have very complex machines. We have industrial robots. We've built the International Space Station. What we don't know how to do yet is build adaptive machines, relatively simple machines that modify their mode of operation when the real world changes what it throws at us. But we do know of one person who's managed to produce untold numbers of adaptive machines, and she's been doing it for billions of years. Who is she? Mother Nature, right? So there was a revelation in robotics a few years ago which said, instead of us trying to sit down and build adaptive machines by hand, let's take a step back and be a little bit humble and allow Mother Nature to do what she does best. But now we're going to ask Mother Nature, instead of producing animals and plants for us, as our ancestors have done for tens of thousands of years, we're going to ask Mother Nature to run an evolutionary simulation in a supercomputer and evolve useful and adaptive machines for us. That's the idea of evolutionary robotics. And when I graduated from Canada, I went to do a master's degree at the University of Sussex in Brighton, England, where I learned about this idea of evolutionary robotics. And I'm using my little cartoons here at the bottom to show you how this works. Basically, we're going to evolve simple robots into complex robots. But instead of trying to explain to you how that works through words, I'll show you a short video.
Die Auslese war hart. Doch jetzt ist sie da. Die stärkste Technik aller Zeiten, gnadenlos günstig. Saturn, wir hassen teuer.
Okay, a little bit of a commercial for Saturn cars. Obviously, this video is not from my lab. I stole this from Saturn, but it gives you the basic idea of how evolutionary robotics works. So after learning about evolutionary robotics during my master's program at the University of Sussex, I was really excited about this idea and the potential of evolutionary robotics to give us adaptive machines. So I moved to Zurich, Switzerland, and started a PhD program at ETH in Zurich, where I was able to really get my hands dirty and start to evolve my own robots, and I'll try and show you those. So a little bit simpler than the robots you saw in the Saturn commercial. Here's some of my evolving robots. They have a very simple mission. Their mission is simply to move into the screen as quickly as possible. And what you're watching now is evolution in action. This is running on a supercomputer, and the supercomputer is running a physics engine, like you would find in most modern video games. And it's running this evolutionary simulation where it's trying out these robots. The robots that move a little bit faster into the screen, the computer keeps, and the robots that move a little bit slower, the robot deletes and replaces with randomly modified copies of the robots that survived. So you'll see that our factory of ideas here is producing a lot of weird and wonderful creatures, most of them which we would like to put out of their misery, but some of them, for some strange reason, manage to walk quite a bit into the screen. The surprising thing about a lot of these robots is they don't look anything like what we see in nature, right? So we can use this evolutionary simulation as a crank to churn out new ideas that Mother Nature might not yet have found in biology. Okay, so that's evolutionary robotics. So I spent 4.5 years at ETH working away at these simulations, and after a lot of blood, sweat, and tears, I managed to graduate. So I went from being Mr. Bongard to Dr. Bongard. Now that I had my doctorate, I came back across the Atlantic Ocean, this time to the United States, and took a postdoc position at Cornell University in Ithaca, New York. Postdoc is basically sort of the waiting area before you get a job to become a professor. So I spent 3 years as a postdoc at Cornell working with Hod Lipson on a project for NASA, and we have a couple people that are going to tell us a little bit more about NASA's ideas shortly. NASA asked us to try and come up with robots that they could use for methods of last resort. What happens if NASA sends a robot probe to Mars or one of the outer moons of the solar system and something truly unexpected happens to the robot? Something that the engineers back here on Earth were not prepared for. They had no contingency plan for. That's where we need adaptive machines, machines that can figure out what to do if something unexpected goes wrong. And again, I'm using this cartoon here to give you the idea of how this works. The approach became known after the fact as resilient machines, or for our purposes, we can think about this as dreaming machines, where we have a robot that dreams about itself. And I'm going to walk you through this process, and I imagine these videos are not going to work automatically, so I'm going to run them manually as we go, but I'll just talk you through this briefly. In the top left, the robot is going to dream up an understanding of itself. So the real robot, you can see it in the top right there, but this robot has no idea how it's put together. It's like a human infant. It has no idea about its own body. So it's going to dream up an understanding of how its body works. Once it dreams up an understanding of its own body, it's going to try and now imagine a solution to the mission that NASA gives the robot, which is just to move from the left side of the table to the right side of the table. Not a very difficult mission. So let's start with those three pieces first. I'll show you our robot dreaming. Here's the robot dreaming and coming up with all these different ideas about how it's put together, and you'll notice now it realizes that it has 4 legs, and these 4 legs are arranged around its main body. The robot understands something about itself through this process of dreaming. Now that it's dreamt that up, it moves on to trying to imagine a particular way to move to meet NASA's mission of moving from the left side of the table to the right side of the table. Here's the idea that our robot has come up with. The physical robot, it hasn't even moved yet. This is all going on inside its mind, if you like. Now that the robot has an idea about how to move, it's going to try it out in reality. Pretty creepy, isn't it? We had an undergraduate student who was working in the lab when we turned on this robot for the first time, and he was scared silly. He said, that's an evil starfish. So that became the nickname of the dreaming robot, the evil starfish. So despite its creepiness, we have a robot now that through dreaming and imagining figures out how to complete a mission on its own. That's step 1. Step 2, however, is the important part, which is the adaptation step. So now, what happens if something goes really wrong with our robot? So we sent in a graduate student with a screwdriver, and he maniacally pulled off part of the robot's leg, but we didn't tell the robot that it had become injured, and the robot had to figure this out on its own. Suddenly, all of the sensory information that our robot was getting was different. All the robot knows is that something went wrong. So how does the robot know what went wrong? It goes back to dreaming. And remember that this is the best understanding that the robot has so far of how it's put together. Comes up with this idea, which happens to be the right idea, but partway through the dream it comes up with this idea that its leg shrunk in size, but that doesn't make physical sense. So it throws that idea away and comes back to this idea which matches all of its physical data, and the robot says, aha, something's happened to me. I now have 3.5 legs rather than 4 legs. But the mission that NASA has set for this robot hasn't changed. The mission is still to get from the left side of the table to the right side of the table. So the robot adapts. It comes up with a completely different way of moving, which matches what the mission is, right? Imagine a robot probe on one of the outer moons of the solar system that comes in a little bit too hot on the landing and suffers mechanical, physical damage, right? This is the situation. The robots now come up with a way of recovering from this, and it tries out this idea that it came up with, and it's an imagination. So this robot isn't going to win a Dancing with the Stars competition anytime soon, right? Kind of feel sorry for this guy limping along, but he does manage to get from the left side of the table to the right side of the table. So imagine we send up a very expensive probe into the solar system, and something seriously goes wrong, where there's a serious chance that the mission is going to be completely scrubbed. Could an adaptive machine recover some of its own functionality and carry on with the mission using some of these evolutionary ideas? So that's the Dreaming Robots project that we carried out at Cornell. And when I finished that project, I took a little bit of time to write a book with one of my former PhD advisors, Rolf Pfeiffer. So if you're interested in some of the ideas I'm talking about today, please go find our book, How the Body Shapes the Way We Think. So after finishing at Cornell, I was very lucky to get a job as a professor at the University of Vermont, which is in Burlington, Vermont. And soon after starting there in 2006, I hired some grad students. So now my team of people is growing. After being at UVM for a few years, I was very excited to get an invitation to come to the White House and meet President Obama. This is a cartoon of my wife who's sitting right down here. She's got beautiful red hair, so she came along with me to this very special event at the White House. When we got there, unfortunately, because of security concerns, they told us the hour before we were supposed to go to the White House that only the scientists were allowed to go and their spouses were not allowed to go, which, as you can imagine, was pretty frustrating for Jess. So I took one of her red hairs with me to the White House and left it there, so part of her at least got to go to the White House. Okay, so I wasn't the only one to get an invitation that day. There were 94 of us that were invited that day, and all of us in this picture are junior scientists or engineers or doctors that are doing some form of research. And not only are we doing research, but we're also trying to bring our research from the lab out to the community, like some of us are doing here today. I was very lucky to get to stand right next to the big guy himself here. After the photo, he took some time to chat with us, and he urged all of us to, again, take our ideas out of the lab and bring it to the people, to the community, and get people involved in what we're doing. So I took that inspiration back to UVM, and I had a brainstorming session with my graduate and undergraduate students and said, how can we bring our research to the people? And after quite a while, we came up with an idea which was to reverse that idea and bring people into our research. And that's my big idea that I want to talk to you about today, which is a related idea to evolutionary robotics, which is crowdsourcing robotics. So my big idea as the years go forward is to try and bring together more and more people with more and more computers and put those two things together and have this combined team of people and computers design, 3D print, and put out into the world as many robots as we can to solve as many different kinds of challenges as we can. So we've just gotten started on that journey, and we've called that project Ludobots. So Ludo is Latin for play. So the idea is to introduce people to this concept by having them enter our virtual lab and play and move into more and more of the research side of things. So I'm going to show you a short video here. This is the actual software we're going to use in the master class shortly after lunch. So let me show you this video of how this Ludobots project works. It's actually embedded right in a web page. I showed you the URL, and you create a robot by literally connecting the dots. So this is also known as the DotBot project. So here you can see a student designing a robot. Once the student finishes designing the robot, they're going to click the green Go button, and now their computer is going to take over, and now the computer is running that evolutionary simulation. So students design and computers optimize or find brains for these robots so that they move as far as possible. This has all been occurring on the web. We've had several thousand people do it so far. So here you can see a whole bunch of people designing and now a whole bunch of computers evolving or optimizing these robots together. So it's a relatively humble first step, but this is a way towards crowdsourcing robotics. Okay, so that's sort of step one. It's very, very simple to get started. Step two is the play part of things. So step one is draw. Step two is play. This is, again, something you can try out on the web. The idea here is to be inspired by animals that you see in nature and try and create robots that do something similar to or perhaps different from the way the animal does it. I've got a bunch of videos here, but I'm short on time, so I'm going to show you just one student project that's come out of this particular project. This particular student was inspired by gibbons, and here's a gibbon doing what a gibbon does best. This is brachiation, swinging from limb to limb. The particular primate species that's in this room right now is not very good at brachiation. You can get better, but it takes years of practice. Gibbons are gifted at brachiation. So this student wanted to make a robot that brachiates, and this student came up with this idea. Here you can see the student making the robot in the simulator. This robot doesn't look anything like a gibbon. We weren't sure what this student was actually doing. The student is now making a number of metal bars between the robot and its food, which is the cube that you see here. And this is what evolution came up with. It's brachiation, swinging from limb to limb, but in a robot that doesn't look anything like anything you would see in nature. So I thought this was a beautiful contribution of this student that took an idea from nature and thought outside the box. How could we generate this behavior, but in a different way? So that's something else you can play around with. I'm happy to share that URL with people after the fact. Just this past year, we've launched step 3 of the Ludobots project, which is coding. So now if you're still interested in evolutionary robotics and you know how to write some computer code or you're interested in learning, you can go to reddit.com. We now have this step 3 hosted on Reddit, and it's organized like an online course, and this picture here is a visualization of this course. You start at the red dot, and then these blue dots are a series of programming assignments. And by carrying out these programming assignments, you gradually build up an evolutionary robotics simulator on your own machine. The green dots that you can see here are students contributing solutions to each of these programming assignments. This was 1 week after launch last August, and the course has since grown to look like this. And I think the tree is actually larger than that now. So you can see a whole bunch of student contributions now. You'll also notice some dark blue dots there. Those are new projects that have been thought up by students and added to the course. So I started as being the only instructor for this course, but now there are other students that are contributing material and teaching new students who are fresh to the course. So this is a way, again, to involve lots of different peoples and lots of different people and computers to collectively design and build as many robots as possible. The last step, which we're hoping to do next year, is the discovery step. So for the students who have now gone through the first 3 steps and have written their own evolutionary simulation, can we get them to now help out as junior scientists on our research projects that we're doing in our lab? So the idea is visualized here. Imagine we have you and 2 other users. You have written some code that simulates the 4-legged robot you see in the center. Another user has created a different 4-legged robot, and user 2 has created a 6-legged robot. And the 3 of you on your own computers have simulated these robots and come up with different results. Some of these robots happen to move faster than others. Why is that? We can bring all of our results together in this online course and together analyze the results, and hopefully, in the not too distant future, we can all collectively write and publish a research paper together. So that's where we're hoping to go with Ludobots. So just to finish my presentation, I've shown you a little bit about where I've been and where I am. Here's where I hope we're going. How many of you know how many robots there are on the surface of planets in the solar system at the moment? There's some NASA specialists here who might tell us a little bit more about that later. Anybody know? You? More than 10. Okay, that's a pretty good guess, right? It's amazing that we don't know, right? We've already started to colonize the solar system with robots. So what I would like to see happen as the years go forward is to involve as many people as possible in this exciting colonization effort that we've already started. Can we, as a group back here on Earth, design different kinds of robots? Perhaps we send a 3D printer to another planet and it prints out our robots there and tries them out. Assuming we could do this as the years go forward and the decades go forward, my very long-term vision, like a lot of people, is can we terraform some of the planets or moons in our solar system? Could we make other places suitable for human and animal and plant life? Can we make a backup of life that's evolved on this planet in case something goes wrong on this one? The very famous astrophysicist Carl Sagan, to paraphrase Carl, he said, Earth is life's nursery, but we can't stay in the nursery forever. That's my big vision as well. Thank you very much, and I'll see you for the master class this afternoon. Thank you.